What if you needed a filter, not just accurate, but extremely accurate? A filter capable of selecting one frequency with incredible precision. The secret lies inside a tiny piece of quartz crystal. In the previous lesson, we learned how SAW filters use acoustic waves traveling across a piezoelectric surface to achieve compact and highly selective RF filtering. They are widely used in smartphones and many wireless communication systems. However, some applications require even greater frequency precision and stability than SAW filters can provide. Communication equipment, laboratory instruments, and narrowband radios often need filters with extremely narrow bandwidths and exceptional frequency accuracy. This raises an important engineering question. How can engineers build filters that isolate frequencies with extraordinary precision? A crystal filter is a highly selective RF filter that uses the mechanical resonance of a quartz crystal to pass a very narrow range of frequencies. Quartz is a piezoelectric material, meaning it converts electrical energy into mechanical vibration and vice versa. At its resonant frequency, the crystal vibrates very efficiently, allowing signals near that frequency to pass with very little loss. Because quartz has an extremely high quality factor, crystal filters provide much narrower bandwidths and better frequency stability than most LC filters. Intuitively, imagine striking two different bells. One produces a short, broad sound, while the other rings with a pure tone that lasts much longer. The second bell is much more selective in the frequency it produces. A quartz crystal behaves similarly by resonating very strongly at one particular frequency. Physically, consider an amateur radio receiver designed to receive a weak narrowband signal. A crystal filter centered at the receiver's intermediate frequency allows only a very narrow frequency range to pass while strongly rejecting nearby interference. This enables the receiver to separate weak desired signals from stronger neighboring transmissions. Mathematically, the crystal behaves as a very high Q resonator with an extremely narrow resonance curve. Its equivalent electrical circuit contains inductance, capacitance, and resistance that model the crystal's mechanical vibration, resulting in outstanding frequency selectivity. Crystal filters are widely used in communication receivers, amateur radio equipment, military radios, laboratory instruments, frequency standards, and precision measurement systems. They are especially valuable in intermediate frequency stages, where narrow bandwidth and excellent selectivity are required. Compared with ordinary LC filters, crystal filters offer significantly better frequency, stability, and much sharper filtering. Although newer technologies such as digital signal processing perform much of today's signal filtering, crystal filters remain important wherever highly stable analog filtering is required. Understanding crystal filters demonstrates how mechanical resonance can achieve remarkable frequency precision in RF systems. They are an excellent example of how physical properties can be used to solve challenging communication problems. A common misconception is that crystal devices are used only to generate clock signals. In reality, quartz crystals are also widely used as highly selective filters in many RF and communication systems. In the next lesson, we'll explore impedance matching in filters and learn why even a perfectly designed filter performs poorly if it is not properly matched to the surrounding RF circuitry. In this lesson, we learned how quartz crystals create highly selective RF filters through mechanical resonance. We also saw why crystal filters provide exceptional frequency stability and narrow bandwidth in communication systems. In the next lesson, we'll explore impedance matching in filters and discover why proper impedance matching is essential for maximum RF performance. If you found this useful, like the video, subscribe, and follow for the next lesson.